Shaojie Chen, who is here actually talking to us about the DMD-based multi-object spectrograph. She's here judging on behalf of that team.
Okay, everyone, I'm Shaojie Chen. About the DMD-based multi-object spectrograph on behalf of the team. So I'm going to talk about what have been happening in the lab. So what we have been doing is to prototype the next generation spectrographs for either space instrument or ground-based telescope. So first, what is multi-object spectrograph? So compared to the traditional long-slit spectrograph, multi-object spectrograph basically can observe hundreds of objects simultaneously. That is, it can significantly increase the efficiency of observing time. So everyone knows what's the observing time, how competitive to get the observing time. So that's meaningful. So there are many ways. There have been a couple of ways to do the multi-object. So like very traditional way to use laser to cut multiple slits on the physical mask, or use the ring precision like fibers, like the DMD-MOS, or could be some very complex organic, customized organic slate, DMD-MOS. Definitely, there could be also for the maps based on the macro shatter array, but this is basically millions of macro shatters can be controlled open close to mimic the slate. But this component is completely customized for NASA for the GWST their spec. So it's very expensive and not affordable for other instruments. But we are really inspired by this concept. So what we do is we come up to the DMD. So what is DMD? DMD is digital Micromirror device. It's very commonly used for like projectors or other commercial equipment. So basically, it's an array of Micromirrors. It can be controlled to tip and tilt to different directions. So within, okay, this could be approach to mimic, to generate the slate for the spectrograph. So let's come to the motivation for our group. So we just got this could be a very efficient way to do multi-object spectrograph for ground-based telescope, or could be great potential way space-based multi-object spectrograph. So that is basically very like emotion behind our projects. So this figure gives you the concept of how the DMD works. So basically, on the focus of the scope, because it's mirror, it reflects light to the imaging channel or to the spectral channel, and each mirror can be controlled. So if you look at the left-hand figures, there's some blanks that is the objects. You get to the spectral channel that is working. The imaging of the camera, just observing the rest of the field of view. So that is it can do both imaging and spectral simultaneously. So the concept is beautiful, but it's not easy. Since DMD is really commercial components, but what we want to use it for the science instrument. So that's why we spent lots of time to test the DMD in the lab to understand, okay, what's the scatterized what's the efficiency of the DMD to fully understand how the DMD performs. Is it okay for the science instrument? That is what we have done in the past several years. And we also have students do the on-site testing to get the image of the DMD and see how the image quality can degrade after the DMD. Also have students working on the algorithm for the data calibration and mimic the spectrum of multi-objects. So we have done lots of work, and then we get confident. Thought, okay, should be possible, and then we totally customize on spectrographs based on the DMD. This is the optical design I did a couple of years ago, and it's based on the Hubble Intertelescope. And this is the DMD spectrograph. It's basically the same as the concept. We have the imaging channel and the spectral channel, and also we adopted very advanced component of the prism plating prism as the dispersion for this system. And then we get everything manufactured and in the lab, because okay, everything just performed as expected without we didn't make any mistake. And then we just encouraged. So after that, we thought we should do moving forward. And then last year we got some seed funding grants to support us to moving forward. So it's a 2 years project. So the goal is we are going to do very precise alignments in the lab and get everything ready to combine or to work with the telescope. So this is just a project structure based on the seed funding grants. And the PI and the Shaojie Chen is the co-PI. We also have King and Suraj and Mark involved. In the meantime, we really rely on the students and some parts of we need to subcontract to make the project can go very efficiently. So the goal of this project can be divided into two phases. The first phase, we are going to finish very precise testing and the calibration and fully calibrate the wavelengths, etc. in the lab. And the second step is we are going to combine the DMD spectrograph with the Hubble Intertelescope and try to get the data for the size. So from this slide, I just show the progress after we get silicon, starlight silicon. So this just gives some concept, okay, what it look like on the bench, and Sarah and Ivy lots of work, especially that they lots of alignment in the lab to get the very initial imaging image of the imaging channel. So this is the on the left side is combined series of 3x3 mirrors, and in that field we just slate the mirror to the image. That's why you can see the white spot on the right. You can see the black hole. That's the mirrors relate to the spectrographs to do the dispersion. And from this testing, we can see, okay, the slate is pretty good, but it still have some room to improve. That is, we are still trying to make it better. And so this is the image of the spectrum channel. So why is this short dispersion? Because we insert the filter. So it's still based on invitation brace, and we insert the filter, the narrow filter of about 10 nanometers. That's why you can see very short spectrum based on invitation brace. And in this way, we can see how the spatial resolution look like. And on the right, we also try use different mask on the DMD. Like the first one, we use intermediate slate to mimic the long slate, but the meanwhile, we can also see the gap between the small dots and to identify, okay, the spatial resolution is good. And also the mercury spectrum based on a couple of the slates. This looks good. So by showing this, we just like to know, okay, from based on the current setup of the system, the image quality is really good. It's really promising. And I also try to use neon and the mercury RPF to do the wavelength calibration. And here you can get a taste of what's in the multi-object spectroscopy look like. And meanwhile, we have the work study student working on the software development. This is the very basic control software because we just start from the software development. And we have two tasks. The first one, we just try to control both the imaging channel and spectral channel cameras by setting explorer and image and etc. On the right hand side, it shows the interface to control the DMD. So with this display has three electronics, and we just want to get everything controlled by the center interface. And that's what have happened in the since last summer. And just recently, we start to work on the system level development since we really want to get everything ready for the integration. So this part of work is led by Mark. I have worked to Mark to system level design. Yes, it does.
Thanks, Shaojie. Hi, everyone. Mark Barnett. I'm one of the technical engineers here. I work most on the DMD-MOS program and space telescopes and working on this as well. So I'm going to give the two slides on the least scientifically interesting aspects of this program. So it's amazing the work that Shaojie has done and the students, and a few others. I got brought in just sort of late in the game to look at the system. That's my sort of background as a systems engineer. So see all the different parts of the system. We have the software. There's the car observatory that tells us what the CDK20 that we're going to mount this on, and the system itself that has been really developed and tested. How do we make it a real instrument that we can use on sky in actual practice? So I'm trying to look at all the different pieces and sort of put together a really simple diagram to understand what are all the parts that have to work together, what are the interfaces that have to work between each part of it, and what are some of the other things that we haven't thought of yet, and we're turning a benchtop piece of equipment into an on-sky real instrument. So yeah, things like what is it like in the dome, what's the environment that we're going to do observing in, how cold is it going to be, how hot is it going to be, what effects is that going to have on the design. We've seen a few things we'll probably need to add in terms of like heaters and fans and thermal cooling, and enclosing everything to be weather tolerant, etc. So it's really not that much more than taking the benchtop instrument and making it work in an enclosed system that can be portable and brought to places, and in theory, manufactured and distributed to other places for use more broadly. That's really it. I just said those two slides.
I don't think that is simple. So there are a lot of things we need to consider. Yeah. So we try our best to make it easy to operate at the observatory. So based on what we have done, we really feel like it's very promising to apply this new technology or innovative technology for the science. No matter either the space telescope or the ground-based telescope. Also, I mentioned like I think they're a good time to do this prototype because in Sharp Lab we have great team and we have launched the space telescope successful last year. also we have been working on the slicer based technical field tools for the Gemini for many years. Yeah. Okay. So as you have time, this is so and also this project is a good skill for students and postdoc work together and also this is very close to the end. That is the goal of the next phase. We are going to find the DMD spectrograph with the telescope. This is our hopefully we can get some data for it. And I think that is also the spirit of the seed funding. Hope we can get very good evidence to approve the external funding. So, and I want to thank you everyone working on this project and Team Azure as well. So I will stop here and I'm happy to take questions. Thank you.
After we.
I know. Yeah, sure.
So with all these little mirrors, there must be some diffraction.
Yeah.
Does that degrade the spectra? Does it make weird PSFs or is it negligible?
That's a good question. So, yeah, actually, that is it on the image plan. So we need to do some simulation to make sure on the DMD surface itself can meet the size requirement because that is the first critical surface to impact on the size the spatial resolution that we use that. Yeah. And as once they integrate the image quality, if you do design simulation properly, it won't. But the scatter light from the very small bit structures that streetlights and also decreasing the efficiency. That's the technical issue or concerning. But the good news is there. I have searched that there are a couple of groups working on the DMD optimize itself. They just trying to bring some recoding on the DMD. And then the efficiency can be increased a lot. Currently, we just tested the shell that is 70 something, and from the paper is that 90%. Then it's really great for the size. Go back and say your question.
And I it's a more conceptual question that you if the light coming in, then the DMD is flat, so it sends it either to this way or this way, and if something is broken, sends it back into the telescope. But I'm sort of, I guess naively, I would have thought you would have such that the mirror, if it's in its relaxed state, makes an image, and that you just turn it only to send it to the spectra or the other way around. But you seem to always move the mirror one way or another, right? Either to the left, to the imager, or to the right.
Yeah.
Spectra. Is there a reason for that, or is it just? I also don't know how they work. Do you continuously have to power them to move them one way, or you just move them and then they're fine, they stay there?
I think that it's it depends on the physical feature of the DMD itself. So once it works properly, it's only two angles, either left or right.
Yeah.
But if let's say the mirror is broken, it's going to reflect. So that means that it will reflect light back to the cluster.
But that's not so good, right? Because then the internal reflections.
Because if there's no optics between the mirrors and all far enough between the DMD and the luster.
It's got banking stuff.
And also that's kind of part of scale light. If a couple of them happens, it's all still like.
You have a sense of put it on the half meter, the parking three, and how faint to the star do you think?
I can tell you what's the efficiency of the system itself. I need to talk to astronomers. That's the
Yeah.
we need so I can really understand the whole system. So that is for the optical and it's actually
We can find the future, so I think.
Yeah.
And all the costs that you can do a lot of them on that.
Yeah, I mean, I think it is. Yeah, there's that, I think it's very simple. But it's very. The trade. But I think that, yeah.
Cool. Any question? Wonderful. Let's thank both of our speakers again. All clear for next week if you are something to talk